Okay, everybody, welcome to the first post-pandemic in-person EAS lecture night here at Chabot. Yay!
And how do I make sure?
Well, what about like 3 years since we've seen each other in person in a lecture night meeting by East Bay Astronomical Society here at the Hubble Space and Science Center in Oakland. And so a very, very welcome to everybody in person here at the lecture hall. And I guess to people in online land, you're missing something, i.e. the in-person meeting. We have just a couple of infos from the club before we get started. And one of them is that we will have Deborah coming quickly telling us about ideas of upcoming eclipse events.
So it's all very good to see you. I want to tell you about an opportunity that we're about to make. We are about to rent or get use of a parking lot in Winnemucca for the Saturday, October 14th annular eclipse. We'll get you more information through the EAS newsletter and through our through emails. I also want to urge you to buy your EAS t-shirt because one of the requirements to getting into the parking lot for the annular eclipse is that you will have to wear your t-shirt. So thank you very much.
All right, it will be your ID card to get into the event to be wearing your East Bay Astro t-shirt. Okay, we have anything else? Go ahead, Rich.
Thanks everybody, first of all, for showing up live. I had no idea in advance how many people were going to show up here. I didn't know if it was just going to be 5 board members and our speaker, but it looks like we've got the usual count of EAS members attending this event between on-site and online. So it looks like it was worth going through the effort. And I really want to thank everybody, though, who made the effort to come to dinner with the speaker tonight and also to show up here. The only other thing I wanted to mention is for those of you interested in our Barcroft high altitude observing event in August, we're filling up. We've still got a few spaces left. And so if you're interested in the Barcroft event, come talk to me about it after the meeting. And I'd be happy to fill you in about what that's all about and give you instruction on how to get signed up if you're interested. And that's it from me. So.
Right on. So in absence of our meeting coordinator and speaker coordinator, Dave Rodriguez, who usually does the job of introducing our featured speaker for our evening presentation, I'll step in. He's out traveling. So I am welcoming Dr. Adrienne from San Francisco State University to give us today a talk about globular clusters and the pale blue dot, how that goes together. She will surely explain to us in her talk. And for all of us amateur stargazers, who doesn't know and who doesn't like a globular cluster in one of our big telescopes here at Chabot Science Center? So they're beautiful to see. They're one of the older structures in the Milky Way, and we're going to learn more about them tonight. Quick info about the speaker. Dr. Kuhl is native of New York and got her undergraduate degree in physics at Yale and spent some time in medical imaging and electrical engineering, and only then took the turn towards astronomy, completing her PhD at Harvard, came to California for a postdoc at UC Berkeley, and now teaches at San Francisco State University. So Dr. Kuhl has her mic wired up. So with that, please welcome Dr. Kuhl to talk us about globular clusters.
Thank you very much. Am I being, I've got a mic on here, so I'll try to talk quietly so I don't blast it. Thank you so much for the invitation to talk tonight. I
am especially happy to be talking to the East Bay Astronomical Society as a resident myself of the East Bay. I live in Oakland. And I was checking through my notes and files and saw that it's 13 years since I last got to speak to the East Bay Astronomical Society. So it's lovely to be back. Let's see, do I have some slides? There we go. Yeah, so I'm going to talk today about the research that my students and I have been doing at San Francisco State for more than 20 years now. And then, yes, I want to spend a bit of time talking about an organization that my students and some fellow faculty and I co-founded a few years ago called Astronomers for Planet Earth. And I'll say more about how that came about as I go. So next slide. That's all good. There should be something before that. Oh, there we go. Okay, so I'm going to spend a little bit of time talking about what are globular clusters and what they're good for, and then a bit about their dynamics. So I'll say, speaking of them being beautiful, really part of the reason I decided to study them is because they're really cool looking. And then I discovered they're also really fascinating, just fascinating objects for so many reasons. Partly, as you said, because they're very old, the oldest identifiable things in our galaxy. Also because, how does a ball of stars that's, a ball of a million stars hold together, and how long can that last? And is it stable? And there are all kinds of interesting questions one can ask. And it turns out, as we'll see, that surprisingly, perhaps, binary stars play a pretty important role in their dynamics. So that's kind of motivating for my own research. And then, as I said, I'll say a bit about the perspective that astronomy brings on our own planet and what's happening right now, and the genesis of the organization Astronomers for Planet Earth. So now I'm ready for your next slide. Okay, so what's a globular cluster? Let me see hands. Who's seen a globular cluster here? I think I'm going to see hands in every. Okay. Any favorites? I'm just curious. Favorite globular clusters?
M4.
Nice.
M5.
Sagittarius. M5. Okay. Okay. So yeah, this is one of my favorites. Unfortunately, not visible from here, but my favorites because it really gives perspective, because it's right next to the Small Magellanic Cloud. And this is 47 Tucani. And I'll just tell a little story, which is when I was in graduate school, I had a few observing runs in Chile, in the mountains in Chile, the U.S. National Observatory there, Cerro Tololo. And one evening I went out and I saw what I thought were the Small and Large Magellanic Clouds, and it was gorgeous, and I thought it was really fantastic. And then I went out a few hours later, and the humongous Magellanic Cloud was there. And it turned out that what I just assumed was the small one was this globular cluster, 47 Tuc. Very easy to see, naked eye. And there's the Small Magellanic Cloud for scale next to it. The Large Magellanic Cloud comes up a few hours later and is way bigger than that. So big balls of stars, hundreds of thousands, in some cases, a couple million stars. Next. So really, you might say one of the first claims to fame of globular clusters is the role in figuring out where we are in our galaxy. So if you go back more than 100 years now, people had worked really hard to try to figure out the structure of the system that we live in. But if you try to do that by counting stars, we're right about here. If you try to do that by counting stars in our vicinity, which various people did, Herschel was one, and Jacobus Kapteyn was another, you conclude that we're at the center, and that it's kind of like a lentil. We're in a lentil-shaped thing. Well, okay, that's not too bad, and that we're at the center. And the problem is that when you try to count stars, there's so much dust in the plane, and we're in the plane, that it's like fog. You can see a certain distance and you can't see beyond it. And so it was not known that we're way, way out in the boonies until about 100 years ago now, when Harlow Shapley, building on work by Henrietta Leavitt, who had discovered a relationship between the period and luminosity of a certain class of variable stars called Cepheid variables. Building on that work, he used that to get distances to globular clusters. And he had noticed that, and I doubt he was the first person to notice this, but that there are a lot more globular clusters in some directions, as I'm sure all of you, many of you know. There are a whole bunch more towards Sagittarius and Scorpius. Over there, there's tons in that direction. And there are others in other directions, but not as many. And so he hypothesized that the center of the globular cluster distribution was the center of the system in which we reside. And I'm avoiding galaxy because at the time it wasn't clear whether the galaxy was the whole universe or what, and what the spiral nebulae were was not clear at that time. Anyway, Shapley used the globular clusters to get the very first, to first show that we are not anywhere near the center, and to make a measurement, because he had measurements of the distances to globular clusters, make a measurement of how far out we are from the center. So I love that story. And another sort of fun piece of that story is that Shapley was then on the wrong side of the next argument, which was, is the galaxy everything? Are the spiral nebulae part of it, or are they separate galaxies? He thought this was everything, and the spiral nebulae were part of it. So there's a lot of interesting history there. Okay, so first claim to fame, used to figure out the structure of our galaxy and where we are in it. Oh yeah, that's where we are. Okay, next. Another thing that globular clusters have done for us over many decades now is acted as kind of Rosetta Stones for stellar evolution. So when you look at the stars in a globular cluster, and this is true of open clusters as well, any cluster of stars, you can see stars in all different phases of their evolution or their life. And when a picture of a cluster might look something like this. This is actually M12, a Hubble image of part of M12. And when you do what's kind of a natural thing for any of us to think of doing, which is, what can we measure about stars, most directly? Well, we can measure how bright they are. And then the next thing you might think about measuring is, well, what color are they? Are they red? Are they blue? Or something in between? And then if you make a plot of those two things against each other, you get a really funny looking distribution. And figuring out and so here's the color and here's the brightness, and analyzing plots like this, which are sometimes called Hertzsprung-Russell diagrams, in which you put the temperature on one axis and the luminosity, intrinsic brightness of the star on the other axis, also called color magnitude diagrams for observers among us, including myself, where we plot magnitude in two different filters subtracted from each other, and then magnitude on the other axis. You get this funny structure, and then analyzing this and figuring out what's going on is a lot of how we figured out how stars evolve. And sort of that combined with the theoretical side and kind of putting the two together. And so what we've learned over time is that what we're looking at in this diagram is, here we've got stars that are much like the sun, although lower mass in this case, because globular clusters are so old that all the high mass stars have burned out. Even stars the mass of the sun have already burned out. Stars that are still fusing hydrogen to helium in their centers are right at the top here at what's called the turnoff. Those stars are now starting to climb the giant branch. They're still powered by hydrogen to helium fusion, but in a different kind of by a different kind of mechanism, in which it's now no longer happening in the core of the star, but in a thin layer around an inert core of helium. And the stars climb the giant branch while they're doing that. They get bigger and bigger and bigger as more and more helium is added to that core of the giant. And eventually, when they reach the tip, they get hot enough in the core to ignite helium, because fusing helium into the next stable element, carbon, takes higher temperatures. So they eventually start fusing helium into carbon. When they do that, they find a new equilibrium, which turns out to be over here. And so the stars then sit here for a while, manufacturing carbon in their cores. Eventually, they run out of the helium, which is what's being turned into carbon. 3 heliums make a carbon. Eventually, they run out of that, and they climb up the giant branch again, climbing what's called the asymptotic giant branch. And eventually, that's kind of the end of the line for low mass stars like there are in globular clusters. They blow off their outer layers, become what we know are known as planetary nebulae. I don't know about you guys, but I always have to say to my students, nothing to do with planets. They look like planets through a small telescope, but these are stars at the end of their lives, blowing off their outer layers and revealing their cores. That core will become then a white dwarf once all the outer layers are blown off. But meanwhile, they're really beautiful to look at, and I'm sure many or all of you have seen planetary nebulae through your telescopes as well. So stellar evolution, yeah, globular clusters have been a wonderful guide to what is going on and ways to test our theories of stellar evolution. The third thing I want to say is dynamically, it's really an interesting situation. Like I said, what is this? This is a ball of like, a few 100,000 or 1 million stars held together by gravity and orbiting the galaxy. There's some 150 or so of these orbiting our galaxy. They occupy the halo of the galaxy, spherical distribution within our galaxy. Well, how does that work? They orbit and they're really old, so they've lasted a really long time. How long can they last? What's going on inside? It's kind of a neat question. So let's look at, here's a little, this is an animation of a n-body simulation, just treating each star as a point mass of a globular cluster. It was made by a theorist, friend of mine a few years back. And yeah, let's start that thing. So what we're going to do here is just kind of fly into the globular cluster and look at it just static for a minute. We're going to actually kind of orbit the globular cluster, kind of see the structure a little bit. They're very, they're much denser at the center than the outskirts. There's a big sort of halo aspect to a globular cluster. This is just kind of looking around. In a minute, time will start passing, and he's going to make the stars start, responding to the force of gravity, and we'll see how they move. Okay. So now you see that just, if you watch any individual star, you can see how sort of complex the motions are. And like I said, each star is responding to the gravitational force of all the other stars. There are also kinds of interesting questions about what kind of structure do you get and the shape of the clusters as a result. It is also the case that through distant interactions, the stars share energy with each other. And the result of that is that the more massive stars tend to wind up with lower velocities, and the less massive stars with higher velocities. And so the massive stars tend to sink toward the center. And then let's see another slide. And that sinking toward the center of the massive stars is such that their predictions were made long ago, sort of theoretically, that you might wind up forming a black hole at the center of these clusters. And in fact, people have been looking and in various cases thinking maybe they found black holes at the middle of these clusters. These days, the idea is that maybe there are sort of 1,000 to 10,000 solar mass black holes in the middle of clusters. And by the way, it is an interesting situation that we have, which is that we have extremely solid evidence that black holes of order 5, 10 to 30 or 40 solar masses exist. Incredible evidence recently from gravitational waves, but we had evidence even before. We have extremely powerful evidence that there are supermassive black holes, millions to billions of solar masses. We've seen images of 2 of them recently, including the one in our own galaxy, but nothing in between. And so that's been a problem for a while that people have been trying to figure out. And where would they naturally be? There's a lot of thought that they ought to live, these intermediate mass black holes ought to be in globular clusters. So people have been looking for them. However, no one has found one yet. I looked for one in the biggest globular cluster in the galaxy, Omega Centauri. We found no evidence for one. Others have looked in lots of places in many clusters and found hints, but nothing that couldn't be explained by like a bunch of neutron stars instead or something like that. So anyway, so this is where binary stars come in, because it turns out that if you have some binary stars in a cluster, what they will tend to do is when a passing star, this is a little illustration here. Here's a binary coming in and a passing star. When a passing star has interaction with a binary, a very common interaction between the three is for the binary to give a kick to the passing star. The binary then becomes it gives up some energy, binding energy, essentially, potential energy, gets lower for the binary, and then it becomes kinetic energy, increased velocity of the passing star. And that you can do computer simulations of this and show it, quite easily. And what much more elaborate computer simulations have shown is that if there are enough binaries in clusters, that they can delay or possibly prevent the formation of these black holes. And so we want to know about binaries in globular clusters. Are they there? What kinds are there? What kinds are there? What kind of periods do they have? What are their properties, and so on. So that's motivated a lot of the work that I've done to try to identify and characterize binary stars in globular clusters, because they might really play a significant role, or they do play, if they're there, and they are, they do play a significant role in globular cluster dynamics. Okay, so I'm say a little bit about sort of how do you find these things in globular clusters. As you may know, even the nearest clusters are pretty far away. They're like, the nearest ones are several thousand light years, like 7,000 light years away, of that order. So there aren't any nearby ones. So binary, and only fairly close binaries will survive in a globular cluster. So we're not going to resolve any. That is, we're not going to see two stars ever. Well, I shouldn't say ever. I mean, not with Hubble, not with JWST, not anytime soon. Okay, so let's. And yeah, there's just a bunch of students of mine who've been presenting posters about all kinds of different things. San Francisco State. Okay, so here's one kind of binary we've gone looking for. And I particularly like this kind because it's made up of the two most common components of globular clusters. Normal stars, like the sun, but lower mass. So that's sitting on the left there. I had a pointer. What did I do with it? Okay, this is it. Okay, a normal star on the left. And in the middle of this disk here, a white dwarf. So a white dwarf is the burned out remnant of a low mass star. Nearly all stars end their lives as white dwarfs, because there are way more low mass stars, low and medium mass stars, than high mass stars in the galaxy in general. So some huge fraction of stars end as white dwarfs. And so there are a lot of white dwarfs in globular clusters. Really hard to see because they're faint. We do see them, and you'll see some pictures in a minute. But anyway, put the two most common kinds of objects in globular clusters together. If they're close enough together, they will interact with each other. And here's the interaction thing, is that this star is sort of filling what's called its Roche lobe, which is its region of gravitational influence. And even though this white dwarf is small, you can't even see it at the center of this disk, its gravitational influence is all around here. And so essentially right here, the white dwarf is exerting a larger force on this material than that star is. And so the material spills over onto the white dwarf. It can't land directly on the white dwarf right away because these two things are going around each other. And so there's a lot of angular momentum. And that's why you get a disk forming initially, but then gradually the material can fall down onto the surface of the white dwarf, and does. And as a result, you get all sorts of interesting phenomena. You get this material gets really hot because the surface gravity on a white dwarf is really, really high. So when stuff falls onto it, it creates a big explosion, a lot of energy is released. And so the accreting material gets really hot. You get X-rays, ultraviolet light, and blue light. And that makes them really stand out in a globular cluster. So let's take a look. Go back. Okay, and I'm just going to show a couple examples here. So just for fun, so this is a picture of Omega Centauri, biggest globular cluster in the galaxy. You can see, I've seen it from a mountain. You can't see it quite from here. It's just below the horizon. Southern part of the US, Tucson, I've seen it from a mountaintop in Tucson by eye. It was really low in the sky, but you could see it no problem. We did a lot of work on this cluster and have found a bunch of cataclysmic variables. Let's just look in the X-ray. Look, it's hard to, you can see it's a lot of stars. It's hard to look, but if you look in the X-ray, this is an image we took with the Chandra X-ray Observatory. We stared at Omega Cen for almost 3 days straight. And in the X-ray, it looks really, really different. And you see many fewer objects, but what you do see have a chance to be things like those cataclysmic variables. And in fact, but then you have to go looking for the star that's responsible for the X-rays. The X-rays alone don't tell you. They could be things in the foreground or background, but we use the Hubble data then that I just showed to zoom in and look for what star has properties that could explain that. And I'll show another example in a minute. But anyway, it turns out these two bright things are cataclysmic variables in Omega Centauri, and so is that one. And a few other things as well. Let me show a specific example where it's a little less complex, but more. So here's another cluster we've looked at quite a bit. This is also in the southern hemisphere, but we were interested in this one because it's very nearby as clusters go. It's the second nearest after M4, I believe. Here's the image in the X-ray. And it's kind of fun to look at X-ray images because it's literally, every dot is a photon, an X-ray photon that was received. Now, this was like a 70,000 second exposure. So, you have to look for a long time to get many X-rays. They're not as nearly as many X-rays coming from these things as optical photons. But so this is what this cluster looks like in X-rays. You can see, okay, there must be something there. Looks like probably something there, maybe something there, and then it starts being, probably the rest is kind of background noise. Okay, and I won't go into those details. But let's now look at the same patch of sky with Hubble, okay? And Rich, maybe you can go back and forth a little bit. So these are aligned. So if you look at this one, for example, this is what I mean about going to the Hubble. Now go back to the Hubble. And so literally it's that star right there. You see that little L? It's the thing at the corner of the L. That star has the right properties, and I'll show it in a minute, to be the source of those X-rays. And we were able to identify using Hubble each of the individual stars responsible. Now, this is with Hubble. If you were looking from the ground, as you probably know, why is Hubble up there? Because you can get such sharper images. From the ground, it's all blurred together. I tried for the first 3 years of my PhD to find these things from the ground and never succeeded. Hubble really makes all the difference. Okay, so, and a fun thing here is that, here's a light week. So in the middle of a dense globular cluster, stars are light weeks apart instead of light years apart. That's still pretty far apart, but it is such that in a dense cluster like this, stars do sometimes collide with each other. And in fact, I particularly like this sort of color, combined images. We made this image using 3 different filters. And you can see these, well, let me just say what a few of these things are. So you can see, for example, these sort of bright orangey red things, those are red giants in the cluster. You can see some bright sort of bluish stars, the bluish green. Those are the ones that on that color magnitude or Hertzsprung-Russell diagram I showed. Those are the ones that are currently manufacturing carbon in their cores. They're hotter. They're still quite bright like giants, but hotter. And so they're bluer. And so that's what those are. But one of the cool things in this image is that this little string of kind of bluish things that are a little fainter than those, these actually are thought to be, they're called what are called blue stragglers. They're thought to be mergers of stars that actually collided with each other. And because they're kind of heavy, they sink toward the center and stay in the center. So, and there's actually various lines of evidence that they really are more massive stars than ought to be in this cluster. They should have burned out, but they haven't because they've only been created relatively recently. So globular clusters are a rare place where stars actually have collisions with each other and near collisions as well. So back to the cataclysmic variables, here are the 5 that we found in this particular data set. And let me just show, of course, we don't just look at image. I love looking at images, but actually, we also make measurements. So let's see if we can see the next slide showing what the measurements look like that help us decide that these really are what we think they are. Okay, and actually this is from yet another data set, but the same idea, but the same cluster, second data set we got following up on that. And so now, just looking at the left panel here, this is the same kind of thing as what I showed earlier. Here's the main sequence, now going much further down than the other one did, basically because we've got Hubble and we can see much fainter stars, even when they're near bright ones. You can see the faint stars. So you see long main sequence. Here's that turnoff here, the giants again. And here are the helium burning stars that are manufacturing carbon. And now we can see white dwarfs. Here is the white dwarf sequence in the cluster. Some hundreds of white dwarfs that we can see. By the way, before Hubble was launched, not one single white dwarf had ever been identified, seen in a globular cluster with confidence, because they're just so faint. They're just really hard to see. But with Hubble, it's totally doable. So what are all these red dots? These are objects that we identified as these cataclysmic variables, 5 of which I just showed you, and then we found a whole bunch more using more recent data. The panel on the right, I'm not going to say much about unless someone wants to hear later. This was another important clue to whether the objects were cataclysmic variables, using a filter that homes in on a spectral line of hydrogen. If anybody's interested in that, I can say more later on. Okay, so I wanted to say one other thing about, one of the joys of doing astronomy, and I'm sure this is true for many of you, is that, you go looking for one thing that you're interested in, and then you find something else that you didn't expect to find, and it's really cool. It's the serendipity in just observing the sky and looking for things is half the fun. And so in this data set, there was some serendipity that was really fun. And you may be able to even see it a little bit by eye yourselves. If you look at this carefully, I mentioned that this particular star is a cataclysmic variable, and you may be able to just barely notice it's a little bit blue. It's a little hard to see. But if you look around, you may see that there are some other much more noticeably blue stars. Like here's one down here. Can anybody see that? Can you see what I'm talking about? Yeah, and so we were like, well, what are those? We're like, what are those little blue stars? Okay. And what was interesting is they were not on the white dwarf sequence, so they weren't just white dwarfs. They do not emit X-rays. We also found that they are not variable in brightness, whereas all these stars, when we made what are called light curves, that is, looked at how they vary as a function of time, their brightness, they flicker. Cataclysmic variables sort of flicker all the time, even when they're not having big outbursts. So these were really, really different. And we got really interested in them. And here's another one. Here's a third one here. And followed them up. And let me see the next slide. And so, okay, there they are. Next slide. And spend some time trying to figure out what are they. And this was the first cluster in which we found a bunch of these. This was one of my graduate students at the time. And so here, now we're just homing in. Again, look at the left panel. This is, again, a Hertzsprung-Russell or color magnitude diagram. Here's the main sequence. Here's the normal white dwarf sequence. These are white dwarfs are now they're made of carbon and some oxygen. If you add one more helium to carbon, you get oxygen. So oftentimes a white dwarf will be made of carbon and oxygen. So these are the carbon oxygen white dwarfs. And this is again a sort of follow-up study to the images I just showed you. The ones with the X's there, those are the 3 that are in the image. These are all additional things we found. And what we concluded that they are is white dwarfs made of helium. instead of carbon and oxygen. So how do you get a white dwarf made of helium? And they are known in the galaxy and outside of globular clusters. And the way you can get them is if they're in binaries, okay? And here's the scenario. You start with 2 stars, and let me just say in anticipation, we not only have reason to think that they're white dwarfs made of helium, but they have companions that are normal white dwarfs and even maybe slightly heavy white dwarfs. So what's the scenario by which you get a white dwarf made of helium? The way you do that is you start with, let's say, a normal star and a white dwarf, not in a cataclysmic variable, just together in a binary. And then the normal star starts, when it runs out of hydrogen in the middle, it starts becoming a giant. It starts expanding, right? Toward the end of its life, it starts expanding. But now, as it expands, it encounters that other star. That other star becomes engulfed by the envelope of the giant. When that happens, the companion star starts falling inward, because now there's friction, because there's an envelope that is plowing through. That friction means it starts falling in. In the process, it gives some energy to that envelope, and that envelope is enough energy is added to the envelope comes off, and then you're left with the core of the red giant with its companion, which in our cases we think are regular white dwarfs. So that core of the red giant, what is it? The core of the red giant. The red giant has not yet ignited helium. So the core of the giant is made of helium. And if this envelope of the red giant gets stripped off before it had a chance to climb all the way up the giant branch and ignite helium, then you're just left with a helium core. And that helium core is effectively a helium white dwarf. And so that's the sort of standard model for how they're formed in the galaxy generally. And there are these things known in the galaxy. And helium white dwarfs in the galaxy have companions. In our case, it basically provides a new window into binary populations in globular clusters, which is really neat. And so we've since then been looking for them and in other clusters as well. And so I'll just say that it's not unique to that one cluster. And it's a new way to find out about binaries and clusters. Okay, so that was a little bit of serendipity and was a lot of fun. Let me turn now. Let me see what's our next slide, Rich. Okay, go to the other. Okay. Okay. All right. So I've spent a lot of time studying globular clusters. This is Omega Cent again, and it's really fun and definitely a privilege. But at the same time, and if you hit a 4 just once more, I think something more will come up. At the same time, I have to say that over the last several years, I've been feeling like, wow, I spend so much of my time thinking about things that are literally quadrillions of miles away. The nearest globular cluster is quadrillions of miles away. Super fun, it's fascinating, it's a privilege. But meanwhile, back on planet Earth, lots is happening. And it started to feel, kind of irresponsible to only spend my time with my, head in the stars, shall we say. And so I started to think, well, okay, what do I do? What is there to do about that? And so now I want to spend a few minutes just saying why I think astronomy really has something to give in the context of the climate crisis and what we're facing on Earth. And yeah, let me talk about that. Okay. So before I do that, I just want to get a sense from all of you. Like, let's see, can we have lights for a minute? On a scale of 1 to 5, I don't know, how worried are you about the climate, about climate change? Just what? And so 1 to 5, like, put up fingers, 1, 2, 3, 4, 5. Can we get a little more? Okay. 1, 2, 3, 4, 5. I see I see, okay, I see. All right. Yeah. Okay. Okay. I see a range, but I'm seeing a lot of 5s, a couple 3s. Yeah. So thank you. So yeah, I'll just say, yeah, I'm worried about it and as well. And yeah, I'll put up my 5. And so, yeah. So what does this have to do with astronomy? It's, let's see. Here's what I want to say about that. Next. Okay. That's fine. Okay. So I'm going to go quickly through the sort of, the alarming situation, right? When I look at a plot like this from NOAA, I get really worried. Okay. So here's 1880 to 2020, difference from, an average between, 1900 and 2000. And, here's the temperature change. And yeah, that looks really scary. It's, there's no question that the temperature is increasing markedly. And of course, and now I just sort of flip through maybe once every couple seconds. And of course, it's not the temperature per se, it's the effect that increasing temperature has, right, on the Earth. The droughts, the storms, the floods, the fires we know well. And you can, maybe I should turn the lights back out so we can see things better, should I? Or I can turn out lights if you tell me which one. Is it the middle one? Thank you. Okay. Yeah. So of course it's the effects. The entire nations about going underwater. And here's what is causing this. I think we all know this. Here's from climate.nasa.gov. The carbon dioxide level going back to 800,000 years ago. And yeah, things were going up and down a little bit, but for a really long time, it never had gone above here. And now we're way up here. So yeah, there's no question that things are rapidly changing, and that temperature change is clearly correlated to it. Okay, so this is actually, there's a very nice book written by climate scientist Kimberly Nicholas that I highly recommend. She grew up in Sonoma and now works at the University of Lund. And she summarizes it really well, I think. Okay, it's warming, it's us, we're sure, it's bad, but we can fix it, really. There are so many solutions. We just need to implement the solutions. So let's take a second at some of the solutions. Yeah, and I think we all know lots and lots of solutions. We need to decarbonize our source of power. We need to keep going. Solar panels, get them everywhere. Get our cars, change our cars. Use trains when we can. Get more trains going. Use public transportation. All these things. We know these things. Keep going. Plant-based diets. How we spend our money really matters. How we vote really matters. All these things. So there are so many things we can do as individuals, okay, and as groups. But let's see. What about the astronomical community? And now I'm going to say, by that I mean everybody who's involved in astronomy in some way. And so that includes me. That includes you. That includes astronomy students. That includes the worldwide people who care about astronomy and pay attention to astronomy. So what does astronomy do for us in the context of the Earth? Well, I think it's fair to say astronomy provides a really special, unique perspective, right? Such a different perspective on the Earth. So there's that, a unique perspective. Also, a scientific approach. We're not climate scientists, but we're used to science. We're scientists and/or familiar with science and care about the scientific approach to the world. And we have so many opportunities to educate. And I know you guys do tons of outreach. I teach a lot of classes. Astronomers all over the world teach classes and do a lot of outreach. And so there's so many opportunities. Yeah. So this is just a series. So speaking of perspective, let's just, yeah, I mean, one of the biggest things is the awareness there's the last one is the awareness of just how small our planet is, and how finite it is. Is there anyone that knows better than us, right? Than astronomers and folks who pay attention to astronomy and study astronomy and love astronomy about just how isolated we are. This is the pale blue dot image taken by Voyager spacecraft back in 1990. I think the next slide just has Sagan's quote, which is so beautiful. Yeah, so how do we, what can we do? We can use that perspective. Next slide. The other thing is that astronomers, have found worlds around other stars, right? And so there's so much in the news about planets around other stars. And that's fantastic. And it's one of my favorite topics in astronomy. I also think it's really important, though, that we all sort of share our awareness that those planets are really, really, really far away. And they're like not places we're going to solve our problems, the problems we're facing on Earth. They're super cool. We learn a lot about the Earth from studying exoplanets. We learn about habitable zones, and we're going to learn so much more over the next few decades. It's super cool. But these are not places we're going. They are just places where we'll learn a tremendous amount. Keep going. So the next nearest habitable planet, well, we don't even know where the next nearest habitable planet is, but the very nearest possibility is around Proxima Centauri, and that's 25, what is that? 1,000 million, billion, trillion, 25 trillion miles away. And yeah, I'm not saying there's some nice, beautiful habitable planet there. No, there's a couple of planets really close to Proxima Cen that, yeah, anyway, long story there. We could talk about it. But anyway, so let's take care of this one. Yeah. Okay, so what can we do? Well, we like I said, we engage in informal teaching all the time. We can bring that perspective back when we're teaching, when we're working on this stuff, when we're thinking about, when we're talking about to other people about it, talk about it, bring the focus back on Earth at the, as part of that. Yeah. In the US alone, 250,000 people, students take astronomy courses. So part of those astronomy courses should be something about what we learn about the Earth and the importance of preserving the habitability of our own planet as part of those courses. And so I'll say more about that in a minute. Planetaria, okay, they're, planetariums all over the world. Something like 150 million people visit planetariums all over the world every year. And what an opportunity, right? To also make sure we include a focus on our planet as part of what goes on in those things, because our perspective as astronomers and astronomy enthusiasts really, really has value. Yeah. So all of that context is what led to the creation, 2019, of an organization called Astronomers for Planet Earth. And this is an international organization that was founded at San Francisco State, but quickly we were found by a group that had exactly the same idea in Europe, and they contacted us, and then like 2 weeks after we launched our website, and we've been working together ever since, and now expanded to 74 countries. Actually, this is old. There's almost 2,000 members now. And so who are we? We're, researchers, students, educators, amateurs, science writers, astrophotographers, kind of, educators, folks working in all kinds of different settings, coming together to help each other figure out, how do we do this? Okay. Doesn't come natural to most astronomers to start talking about this stuff and include this in what we teach. So we need to help each other figure out how to do that. Yeah. And now I'm just going to show a few examples of the kinds of stuff we do. And yeah. So what's the mission? Basically to mobilize and help empower the global astronomical community to take action, to do stuff, to help act, because this is the decade that matters the most. Like, we're here now, we can do something, and now really matters. The UN's panel on climate change has made that so clear. They're like shouting from the rooftops in every way they can, And if scientists don't listen and do what we can, that means something, right? So so it's important not to ignore it. All right, so we want to integrate climate change into astronomy education and outreach, and then make astronomy itself a sustainable endeavor, right? Like take care of our own, clean up our own house as well. And there's a lot to do, of course. And then build a community to educate, inspire, and support each other, because it's not easy to talk about this stuff. No one wants to talk about it. It's not a happy, topic really, but it's important. So we're trying. So we have lots of different ways that we do that. Yeah. Okay, so we got a website. You can find it by going to letter A, number 4E, a4e.org. Is how you can find it. There's a lot of stuff there, and I'm just going to give some examples in the next few slides of what you'll find there. Keep going. Oh yeah. So a whole bunch of very short videos, kind of inspiring, beautiful, lovely videos that kind of use the astronomical perspective to shine a little bit of a light on climate change in a lot of different ways. This is made by a videographer, Steve Agnos, and his wife, Jessa Agnos, who's a master's student at San Francisco State. I highly recommend these if you're doing some kind of outreach. Go check them out, see if you like them. I think they're lovely, and they can be useful as a just 2 to 4 minute little video inspiration. Yeah. We're doing all kinds of different public outreach. Go ahead. What else is there? Oh, there's a series of webinars. So like I said, I'll speak for myself, but this is common, very, very common. Most astronomers, most folks in the astronomical community working in planetariums, doing outreach of various kinds, are not, do not necessarily feel at all comfortable talking about climate change. Maybe they were like, well, I don't have any expertise in that. How do I do that? Well, there's a whole series of webinars to educate ourselves a little more about it, enough so we feel comfortable, and also about how to communicate about this stuff, because it's different. I could talk about black holes all day, but talking about climate change is another story. So there's a whole webinar series. These are all on the web, available on our website. Keep going. We share resources on the website, just teaching materials, and any ideas anybody has, they can share on there about, oh, here's something I tried and worked really well, and things like that. So we have mechanisms to share materials on the website. We're building that up more now. Many members have written lots of articles. You can just plop through all the articles, looking at the carbon footprint of astronomy. Like I said, we need to clean our own house as well. What are our major contributions to that? And also, and they keep going, what's the impact also of climate change on astronomy itself? And there is an impact on astronomical observations. Did a whole open letter campaign urging astronomical societies all over the world to make sustainability a key part of their mission. And that's the American Astronomical Society is beginning to work on it. European Astronomical Society, there's progress on that front. We've been organizing conferences and conference sessions, and just building a community, people to help each other figure out how to do this in our spare time. This is an all-volunteer organization. I know you're familiar with all-volunteer organizations. And so it's kind of haphazard, but we're putting it together. And the next to last slide, and how do we communicate? A lot is done over Slack, but we have an email thing as well, and a newsletter that comes out whenever anybody can get it together to do that. We're trying to raise some money so that we can have that more regular. And then the website is the main public-facing thing, video series on Vimeo, webinars on YouTube, and again, when there's someone available, social media. Okay, so that's it. So Astronomers for Planet Earth, join us or follow us or check out our website. Just interested to hear your thoughts as well about this matter. Thank you for listening. Turn the light back on. Let's see, I forget which one of these.
I'm going to come over with the microphone to you having a question so that for the folks online, we have the question audible to them. So why don't you go ahead?
What interaction, what connection do you have with the people working on the electrical, battery, electrical charges and having that, making things more efficient. That expands. Is there a bridge
Between Astronomers for Planet Earth and, you mean particular,
like development of storage? Of a storage,
yeah.
some kind of, some of the things that are
It's a,
not ready for.
sure. Yeah, no, that's interesting. I mean, Astronomers for Planet Earth has been around just for 3.5 years now. And like I said, we're a kind of loose, bunch of volunteers from all over the world getting together to try to figure out how to do this. So we don't have any formal, connections like that.
Connections.
What we're doing is basically two strands, trying to say, many of us, so many of us are educators in some way or other, right? Informal or formal. And so let's incorporate that into
Mhm.
what we do.
Mhm.
So then that's about adoption. So that's encouraging people adopt that battery, adopt the, see what you can do to address the, to help, address the issue in your life, right? And then on the other side is, let's look at what is astronomy's footprint and
Mhm.
work on that. And
Mhm.
that's an interesting question itself. I mean,
Mhm.
a lot of it is travel. Some is computing, because we do a lot of computing. So there are ways to work on that. But there aren't, formal ties with, but if there's any individual who's part of the group who has knowledge, they share it with everybody else. You know
Yeah,
what I mean?
yeah,
That's kind of how it is. It's a loose affiliation.
Questions in the room, just wave your hand.
The elephant in the room is China. So is that one of the members that has joined your group?
We have a small number of members from Asia, but absolutely. But it's I guess my own feeling about it in general is that I agree with that, there's that's a really important question, but it's also the case that we need to be careful not to be doing this, pointing fingers, right? So if we can show leadership and I'm just say, astronomical community, but let's say the US, can show leadership in that case, that makes a difference, right? If, everybody, people look at what other people do, countries look at what other countries do, all those things matter. And so I just think if everybody can be rowing in the same direction, in the end, it helps. But yeah, I mean, and part of why we want to be worldwide is for that reason. But I'm sure it's, this is a harder problem to face in some countries than others. Yeah.
I have a question from Bruce on the Zoom meeting.
But let me say one more
Oh,
thing,
sure,
if I
go
may.
ahead.
I mean, I think it's also important to know that the US, historically, our carbon footprint in the US dominates, still. And so it's, if you look at the cumulative amount of emissions, we are still hugely responsible. And so, I feel like therefore we have an extra responsibility. But that isn't to say to ignore what else is happening, but we bear an extra responsibility as a result. Yeah, sorry.
Bruce is asking a question about gas clouds and protostars. Gas clouds around protostars, as well as galaxies filled with stars, form a disk in response to the average angular momentum of the material in the cloud. Why are globular clusters spherical instead of disk-shaped?
Oh, it's a great question. And, I'm going to say that to some extent, we don't know the answer yet because we don't actually know yet how they formed. That's an area of current study. Figuring out how things that are 12 or 13 billion years old formed is not so easy. And there's a lot of work on that. But yes, I mean, fundamentally what it means is that the stars had to form before the gas cloud collapsed into a disk. Because yes, gas clouds tend to collapse into a disk. But here's a nice analogy. the globular clusters themselves, right, are not in a disk shape in our galaxy, right? They form a halo around our galaxy. So there's sort of an analogy there. If you think of each globular cluster, itself as one object, why are they not in the disk? Why are they on all these, different orbits? So it's the same idea. The idea is that they formed while the cloud of gas that formed the Milky Way was still collapsing. And before it formed a disk. And therefore, once they formed, stars are really, dense compared to the very, very diffuse gas clouds in the galaxy. They just plunge right through the galaxy, and it's like BBs going through things. They don't see the rest of the galaxy except for the gravitational forces anymore. So why are globular clusters all in random orbits? What we think is that means that they had to have formed while the gas cloud was collapsing before it made a disk. And in fact, that's what we see. The disk is about 10 billion years old. Globular clusters are older, 12 and 13 billion years old. So they formed while it was collapsing before it made a disk. So it's sort of analogous. Yeah.
Great
Yeah.
answer. Good question. If anybody wants to ask questions on Facebook or on our Zoom Q&A, please feel free to do so. Do we have other questions from the room? Anybody? All right, go ahead.
So you mentioned James Webb a couple of times in your talk. I've been following that because it's been on the news everywhere.
Yeah.
It would be interesting to hear how that's affected your group, how the
Mhm.
James Webb and all this new stuff, what's the most effect it's had, or what's the interesting effects that has had?
Yeah, thanks for asking about that. Yeah, so it's an interesting situation. So James Webb, as you know, is primarily focused on sort of red and infrared, and that's its power. That's part of why it's incredibly helpful, because it's two of its main goals are to look at galaxies currently in the process of forming, which are really far away. We're going to use the universe as a time machine and see things as they were when they were much younger, and they're highly redshifted, and so it's very helpful to look in the infrared, and then also to study exoplanets, which of course planets emit infrared rather than visible light. The work that I do benefits from sensitivity in the ultraviolet a lot, and so in that sense, I haven't been chomping at the bit the way many other people have been to use it, I'll be honest. And that's just as well because, a lot of people want to use it on a lot of great things. So Hubble is actually still, for me, the better telescope because of the value of ultraviolet and the very large range of spectral sensitivity that Hubble has. It's also the case that, globular clusters, because they're very crowded, the giants, which are quite bright in the infrared, will really dominate the light and make it harder to see faint stars. And so, yeah, going into the infrared for globular cluster, the only reason, the main reason for my mind to do it is if you want to see the very, very faintest main sequence stars and the end of the main sequence, actually, that's really interesting. And that would be great to do with Hubble because they're really faint and red. And so, and you wouldn't care if red giants blocked out some of the cluster because you can look other places. But since I do a lot of work on trying to find rare objects, binaries, yeah, I'm sticking with Hubble for now.
Questions in the room? Okay, right on. Let me come with the mic.
Thank you. I'm going to try and see if I can put this in the proper form. The study that is going or ongoing right now on finding other galaxies. Is there any evidence of phenomena or finding globular clusters that cluster around these other galaxies?
That's a lovely question. Yeah, so we absolutely see globular clusters in other galaxies. In fact, some, I think it's M87 that there's like 1,000 globular clusters or something. I mean, some elliptical galaxies, which are thought to be mergers of multiple other galaxies, spiral galaxies and others. Some of them have huge numbers of globular clusters. They're stunning. One of the cool things that I think that JWST will help with, and Hubble certainly helped with, is trying to see very young globular clusters. So look into the distant past, and can't go too distant, or globular clusters would be too faint to see. But I think there'll be more more work figuring that sort of stuff out. How do big clusters form early on? Yeah. So I undoubtedly, yeah. Sorry. Oh, I see. Yeah. So, I can't say that I've heard anything yet about that specific thing. It's not easy, it's not going to be easy because globular clusters are bright, but not bright compared to whole galaxies. And so, but I'm sure people will be looking at that. And certainly here's a cool thing that people have been doing lately, and I'm sure there'll be more of this with JWST, is using, in fact, I just read a thesis about this because one of my undergraduates went ahead and did a master's thesis on this work, looking at star forming regions in very distant galaxies, using galaxies that are behind big galaxy clusters, such that you get lensing by the big galaxy clusters, and the galaxy that you're looking at that's behind is magnified by the galaxy cluster. And so you can see more detail. And he's studying star forming regions in very distant galaxies by using galaxy clusters as his telescope, basically. Yeah, it's pretty neat. And it's hard work, let me say, but they're succeeding. So there'll be more. Great question.
We have a question from Celeste Burrows. Hi, Celeste. I'm wondering if you were at Berkeley while Ivan King was there.
Oh, yeah,
And
absolutely.
did you work with him?
He was my postdoc advisor. I was very, very fortunate, I will say, to work with him because I was actually just mentioning this to one of my students. I started working with him in 1993. He had just retired. And so he had all his time to do research. And he was so happy. He didn't have to go to any meetings. He didn't have to do any administration. He didn't have to teach any classes. He got to just do research. And he was one of the people who helped design one of the instruments on Hubble, the faint object camera it was called. And so he had guaranteed time on Hubble. And I had the incredible good fortune to arrive here just as Hubble was being repaired. And so I was glued to the TV watching the repair because I knew, wow, if they succeed in that repair, I'm going to have a really fun 3 years working with Ivan King, who was like the godfather of globular clusters. So he's the person who, back in the 1960s, figured out, based on cluster dynamics, like what shape globular clusters should have, and explained why they have the shape they do based on sort of theoretical analytical work. And so, yeah, it was a real privilege to work with Ivan King.
That's cool.
Yeah.
Very good.
Yeah.
Another question online. Actually, this question was asked nearly 2 weeks ago in anticipation of your lecture. We have a club member, Dorothy Williams, who has been doing wonderful work with her unistellar telescope. And she's always sending me photographs that she's taking through the unistellar. And she was very curious about the one I'm putting up on the screen right now. If you turn around, this is, you may want to dim the light,
Yeah.
Gert. Yeah, this is M12. M12.
Okay. Yeah.
And she was
Nice.
noticing that this looked a lot more yellow
Hmm.
than the other globular clusters she was photographing.
Huh.
And I had a theory about that had to do with the camera, but she was wondering, is there anything particular about M12
You know
that
what?
is different from other globular clusters?
That's a good question. What I don't know offhand, but what I would check first, because first of all, in terms of the stellar populations in clusters, they're all pretty similar in the sense that the dominant light it basically comes from the brightest main sequence stars, the brightest hydrogen burning stars, and those are all pretty similar in globular clusters. And so that shouldn't be too different. But some globular clusters are behind a lot more dust And that causes things to look redder or yellower initially than they really are. I don't remember offhand M12 being behind a lot of dust, so I'm not saying that that's the answer. And yeah, but that's the first thing I would check.
My theory was that M12 has some very bright yellow stars, not just in the foreground, but also in the cluster itself, and that it affected the white balance of the camera.
That is also very possible. So if it's got a couple of giants that just happen to throw things off, yeah, that's a
Yeah.
great idea. That's
Yeah.
that's probably the most likely, because the chances that it's, happens to be one of the very low, low galactic latitude ones, I think is slim.
All right.
Okay.
See
Any
if we have any
more questions? We have one more question. Yeah. Hey, question from the room.
Yes. What are the prospects of exoplanets and in particular habitable exoplanets within globulars?
Oh,
Yeah, it is a neat question. So some searches have been done for planets in globular clusters. And the way they've been done is the transit method, the method by which you look for a star to get fainter in a periodic fashion, just the way the Kepler satellite looked for exoplanets in our galaxy. And the one study two studies that I've seen have found none. And now, admittedly, they weren't, terribly extensive studies. But I think the one that I'm remembering thought that if there were some sort of similar numbers to, what was kind of expected for, compared to solar neighborhood, that they would have seen a few and they didn't see any, like they'd have seen a half a dozen or something and didn't see any. So it's, it's not insignificant. There's two issues for planets, two problems for, planets in globular clusters. First one is globular clusters are so old that there's much, much less by way of heavy elements in them, because they were formed before most of the carbon and magnesium and iron and nickel and all the good, stuff from which things are formed on Earth and rocky planets. Before most of that was made, because we had to wait. The sun, fortunately, didn't come into existence until several billion years after the universe had been around, and the previous generations of stars had manufactured all the good stuff that we know and love here on Earth, and spewed it back out into the galaxy for it to be made into future stars, including our sun and the planets around it. So globular clusters, often have roughly like a 100th as much of the heavy elements. So that's a reason to think that there may be fewer planets just because of that, at least fewer rocky planets because of that. The other issue is that the fact that there are near, in at least some globular clusters, that collisions are not that rare, means that, it's a little more perilous there. Not so perilous that they couldn't, it's not impossible to have a planet near a star. Some might get unlucky, but others could survive. But I think the lack of heavy elements may be a bigger issue. And so it'll be interesting to see, with the study of exoplanets generally, the correlation between metallicity and presence or absence of planets. Yeah.
We have one more question from the room.
Any evidence or work being done looking for evidence of dark matter?
In
No,
globular
in
clusters.
globular
People
clusters.
have looked and not found it. Basically, you can explain so it's kind of a classic thing. So the motions of stars in globular clusters, when you look at them carefully, you can make sense of them just by the stars that are in the cluster. So in contrast, right, to the Milky Way, where if you look at how the Milky Way stars are moving, they're moving so fast that the Milky Way should fly apart, unless there's, like 80% of the mass is something that we don't know what it is, as in dark matter. Not so for globular clusters. The motions that we see are well explained without any significant dark matter. Yeah.
Thank you so much. Rich, want to be closing?
Yeah, I guess so. Thank you so much, Adrienne.
Thank you for the invitation. A pleasure.
And I appreciate it.
A big shout out from the way I was looking at it. We got a wonderful crowd of people who took it upon themselves to be part of the first on-site East Bay Astro meetings here at Chabot Science Center. And shout out to those who are at home online and were on the edge of coming. Come next time for our next meeting.
And the total turnout actually tonight is bigger than usual. So
Wonderful.
not just here, but we had a good home audience as well. So I think we're going to stick with these hybrid meetings for a while. And I hope it worked out for everyone. Next month, our speaker is Dave Erskine, who is also here in the East Bay, good friend of mine. And he'll be talking about his research into something called EDI, which is a way to increase the resolution of spectrographs and using interferometry and some of the equipment he's developed and some of the practical applications for it. And he's given a talk to us in the past in a more nascent period for this stuff, but now he's got some real interesting results. So he'll be checking in with us next month. Randall, do you have something to say? Oh, okay. Very good. All right. Well, good night, everyone. Let's put the lights back on and
Still turned on here. Oh, you are so welcome. It's my pleasure.